In this video, we're going to see how to perform a hypothesis test for the population mean, mu, and we're going to use data file coffee. But before using the data file, before opening the data file, I'd like to just look at the test statistic for hypothesis tests when we're dealing with population mean or mu. We already know about the 6 general steps of hypothesis testing. I said test statistic is probably the only step that is different from a test to another test. P-values, it depends on the distribution. It can be again different. Sometimes we're dealing with T distribution. Sometimes we're dealing with standard normal. Sometimes even with F distributions. So that changes the next step. The conclusion and the statistical inference, statistical conclusion steps are more or less the same again from a test to another test. But here I'd like to copy this, the test statistic. And I'm just going to come to my Excel file. And maybe paste it here. All right. So the first step in hypothesis testing is to develop the null and alternative hypothesis. So in this case, I'm going to just write it down. So the null hypothesis, I'm going to perform a two-tailed type of test. I want to see if mu, population mean, or the average weight in the population, not in my sample here. So here I have a sample of 36 coffee bags, and I have their weights in pounds, the number of pounds that they weigh, each one of them. So what I'm trying to do here, I'm trying to see if for the whole company, if the average weight is equal to 3 or not. So that's the type of test that I'm running here. So I want to see if mu, and mu is basically population mean of the weights, coffee bag weight. If mu is not equal to 3, and here you can put this, you can do this. There are different notations, but I'm gonna do less than or greater than, strictly less than, strictly greater than 3, just to basically denote and not equality, right? You can also use the equation for typing. I mean, you can go to insert tab and add equation, but doesn't really matter. What matters to us is the accuracy of the statistical process here, not the typing here, specifically typing the hypothesis set. As long as you can carry the meaning, that's fine. So this is the hypothesis, the set of hypotheses that we're trying to test. So, and this is the test statistic. So that this one, which we already did, this is step 1. Step 2 would be to basically decide about level of significance. So I'm just going to write it down, level of significance, or alpha. But I'm going to fix it to 5% because most of the time we're going to use 5%. That is the default value unless otherwise stated. So 5% is our benchmark. 5% is going to be our convention, right? From now on. So level of significance, or alpha, 5%. So that's step 2. Step 3 is to find the test statistic. So for the test statistic, we need to find, basically there are some ingredients here. we need the sample mean, we already have the hypothesized value is 3, mu 0, the hypothesized value is 3. We need sample size, we need sample standard deviation. So these are the ingredients that we need before we can measure, before we can compute the test statistics. So I'm gonna start with sample size, or n, and that would be simply count A of my sample, or again, we already know it's 36 of them, so you can simply type 36 if you feel more comfortable with that. It's always better if you use the formula. So sample size, and then sample mean x bar, average of my numbers, average of the numbers here. Next, sample size, sample mean. I also need sample standard deviation, S. stdiv.s of my sample here. And that will give me the S, right? I'm just gonna record mu 0, hypothesized value, or mu. It's gonna be 3. I just typed 3 here. All right. Next, I'm just gonna find the standard error, and then you can do that, or you can just directly go ahead and find the test statistic. It's up to you, but it's okay if you find the standard error. Standard error meaning standard deviation of x, sample standard deviation divided by square root of n. We already know that we refer to this, the denominator here, as divided by square root of n, as the standard error, or the standard deviation for x bar, for the sample mean. We already know this from the distribution of x bar, right? So sample deviation divided by square root of sample size, that would give us the standard error. From standard error, we can go ahead and find the test statistic. I mean, from all these ingredients that we have, we can go ahead and find the test statistic, T, and that would be parenthesis x bar minus mu 0, hypothesized value, divided by standard error, S divided by square root of n, standard error. That would give us the test statistic. So this is for step 1, step 2, step 3. Step 4 would be to find p-value. For p-value here, I'm gonna find p-value lower tailed, upper tailed, and two-tailed. You don't have to really find all the 3. You can just look at the type of test here. We have a two-tailed type of test, a two-tailed type of test, because we are rejecting at both sides. We want the mu, we want our sample mean to be close to 3. If it's too far from 3 at either side, we're gonna reject the null hypothesis. So because of that, because we reject at both sides, we call this a p-value, we call it a two-tailed type of test, and we are going to need p-value two-tailed. But I'm just gonna find 3 of them just to see how we can find the p-value. I mean, different values of p-values for different types of tests. If we're dealing with a lower tail type of test, we are going to, in either case, this test statistic, we call it T. And the reason for that is because this is following a T distribution. We already know this from interval estimation for the sample, for the population mean. We use T distribution. So this is same distribution, T distribution, all right? But this time we're gonna use T dot dist. Before we use T dot inverse, now we're using T dot distribution. And for that, we need, first we're gonna look at the lower tail. Lower tail, p-value lower tail would be the p-value below the curve to the left side of the test statistic. That's the definition of p-value lower tail. P-value lower tail is the area below the curve of the distribution to the left of this point. So here, exactly, we have the sampling distribution of X bar. This is assuming the null hypothesis is true, assuming that it has a normal distribution. I mean, of course, if the sample size is large enough. If the null hypothesis is true, the average, the mean of this population should be at 3. Now you got a sample mean of 2.92. Now, what we are trying to do right now is trying to see if this 2.92 is really far from the 3. If it's far from 3, we're going to reject the null hypothesis. If we don't find enough evidence to say that this 2.92 is far from 3, right, we then cannot reject the null hypothesis. So the whole idea is to basically normalize the distance between the sample mean and the hypothesized value of the population mean. All right. So for this, we're going to convert this value, the sample mean, and find the sample statistic, the test statistic, which is X bar minus hypothesized value divided by standard error. And we just got the test statistic. And this new random variable, the test statistic, will now have a T distribution with n minus 1 degrees of freedom, n minus 1 degrees of freedom, all right? The area to the left of this curve is called p-value lower tailed. The area to the right of this point is called p-value upper tailed. P-value lower tailed plus p-value upper tailed is going to be equal to 1 because that would together they would count as the whole space basically, and the chance of having a number in the whole space would be equal to 1. So p-value lower tail plus p-value upper tail is going to be equal to 1. So I'm just going to come back here. So T distribution. Now we're doing the left side. So X being the test statistic, the T value, degrees of freedom is going to be n minus 1. And then here you need to put, for cumulative, you need to put true. I mean, we're looking for the cumulative distribution, cumulative basically probability to the left of the curve. So if you put false, what Excel is going to return if you put false instead of, if you put true, it's going to give you the area below the curve to the right side, to the left side, sorry. If you put false, it's going to give you the height of this point, the height of this point on the chart, all right? So that's not what we're looking for. So we need to put true here, and that will give you the p-value left side. Now p-value upper tail is going to be 1 minus p-value lower tail because the sum of these two should be 1. And then p-value two-tailed is going to be You just look, if you have a test statistic that is negative, p-value two-tailed is going to be the area below the curve to the left multiplied by 2. So you will have minus 2.82 and plus 2.82. The area to the left of this number and the area to the right of the positive number. Since the curve is symmetrical, it's going to be 2 times p-value lower tail. So the p-value two-tailed is going to be 2 times p-value lowercase in this case, p-value lower tail in this case, because the test statistic is negative. If the test statistic was positive, you should have multiplied this by p-value upper tail. But just to be safe, in general, I'm going to take the minimum of these two and multiply it by 2, and that way we can get the p-value two-tailed, regardless of the sign of the test statistic. All right, so now we have the p-value two-tailed. The type of the test that we are actually doing is a two-tailed test, and we need p-value two-tailed. All right, p-value two-tailed. The step 5, the conclusion step, we just compare this with the level of significance. If p-values, since p-value two-tailed is less than alpha, alpha being 5%, we can reject the null hypothesis. If p-value is smaller than alpha, you can go ahead and reject the null hypothesis. We can reject the null hypothesis, which means, and conclude that. So if you reject the null hypothesis, you reject this one and you take this one. So you are concluding that with 95% confidence, so now the confidence level, we said 1 minus alpha is the confidence level, right? So with 95% confidence, the population mean of weight, the mean basically, mean weight or average weight of the coffee bags is not equal to 3 or is statistically different from 3. So these are different terms that you can, since p-value two-tailed is less than alpha, all right, we reject null hypothesis and conclude with 95% confidence that the average weight or mean weight of coffee bags is not equal to 3 or statistically different from 3. We can reject null hypothesis and conclude with 95% confidence that the mean weight of coffee bags is statistically different from 3. So I'm just gonna make this look nicer. Yes, so this is now our statistical, this is our conclusion, and this is what we, our business conclusion, right? So depending on the case, you may have a business decision to make after making this inference about the population mean, about the weight of these coffee bags, right? So you may have these items might actually come from your supplier. You want to see if you have a contract. You want to see if the size, if the weight of the bags if the average weight is equal to 3. If that is not the case, you may go ahead and fire the supplier, all right? Or you may want to just go ahead and make a complaint about that. So this is one thing. This is basically, this summarizes the process of hypothesis testing for the population mean. Now, before we wrap this video up, I'd like to put this. I'd like to ask you if instead of this hypothesis said, what if we had this? What if we had a one-tailed type of test, where mu less than or equal to 3, and then alternative hypothesis mu strictly greater than 3. So this is, so here we had a two-tailed test. Here, this is a one-tailed test, and it's an upper-tailed test. Upper-tailed test. This is an upper-tailed test, all right? Now, all these steps are the same. The conclusion step, in order to make the conclusion, you shouldn't look at the p-value two-tailed anymore. You should look at the p-value upper-tailed. P-value upper-tailed is not less than, since p-value upper-tailed is not less than, we basically, I'm just gonna say that we fail to reject null hypothesis because p-value upper-tailed, that's what we need, upper-tailed is not less than alpha. It's not less than alpha, and alpha is 5%. All right. What if we had, so let me just take it from here, put it here. What if we had the other way around? What if we had, let me just copy this, paste it here. What if we had greater than or equal to 0 and alternative hypothesis strictly less than 0? So here, this is a lower tail type of test. We are rejecting at the lower side of the distribution. So lower tail type of test. This time we reject because the p-value lower tail is definitely less than alpha. So we need to compare p-value lower tail to alpha. So we reject null hypothesis because p-value lower tail is actually less than alpha 5%. All right, so this is a lower tail type of test. So we take the p-value lower tail, compare it to alpha. If it's less than alpha, we reject the null hypothesis. So we reject the null hypothesis. So our conclusion would be this. Our conclusion with 95% confidence would be that the average weight is less than 3. Our conclusion here, we fail to reject, so we would take the hypothesis, null hypothesis. Here, we actually rejected, right? So this is what we take. Here we would say we fail to reject, we don't have enough evidence to say the mu is strictly greater than 3. We can't say that the mu is greater than 3. It's probably less than or equal to 3.